About physics. In the event of Top Hat not working for one of you guys, we will use the sheet. So, let's see here. If I can find my... We begin with a word of prayer. So, Dearly Father, we thank you for this day. Again, I thank you for this class. We thank you for your creation that you've made for us. And help us to enjoy it. Help us to glorify you what we do this day, Lord. And we just thank you again, Lord, for your many blessings. In your name I pray, Lord Jesus. Amen. So today, I must talk about electric field lines. And so we're going to talk about flux today. What is flux? How do we understand flux? How do we calculate flux? What's the deal with flux? Let's see here. So, there are a couple of basic rules. And those basic rules are the following. All right, so like rule number 1, electric field lines do not cross. Well, except at their source or sink. All right, so like the only place where electric field lines come together is where there's charge. In the absence of charge, electric field lines do not intersect. And then rule number 2, which kind of has 2 parts, I'll say, and it's electric field lines flow out of positive charge, and they flow into negative charge. All right. And so we think of a positive charge as a source of field lines, and negative charge as a sink of field lines. If you also let me just draw a picture. So like, yeah. So here's positive charge Q and negative charge minus Q. All right. So the field lines, the way they work is they go from the positive charge and they flow into the negative charge, something like that. And the direction of the field lines we can think of in terms of the Coulomb field that we talked about last week. So the field lines flow symmetrically in all possible directions out of the charge, all right, in the absence of anything else. But in the presence of another charge, they get bent around, all right? So we kind of have to go with that. So the field line configuration looks something like this here. So the only place these that was supposed to, you get the idea, up to the limits of my artistry here, the field lines, they look kind of more like the Coulomb field out here, but they have to somehow come together continuously. So this is the configuration. Looks something like this. I probably should have started with something easier. Oh well, my mistake. So they flow out. We put little arrows on. So they're flowing out of the positive charge, like so. All right, out of the positive charge, and they go into the negative charge. All right, like that. So let's see here. How many field lines? So in the current diagram, I drew how many? I drew 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 11 or 12. I've lost track. 11. I drew 11 field lines coming out of these charges. All right? And that's a diagram that would illustrate this, right? In principle, if this sets the convention, if I doubled the charges, I would double the number of field lines. All right? If I tripled the charges, I would triple the number of field lines. All right? So the more charge, the more field lines. How many field lines do you draw? Why did I draw 11, not 12? I looked it up in a manual somewhere. It's dictated to me by some sort of secret society. No, I mean, I just drew 11 because I ran out of board space. I mean, honestly, right? So it's just a choice. So you make a choice. Relative to that choice, we have a diagram. And the way way it works is the more dense the field lines, the higher the magnitude of the electric field. All right, so like if I think about taking, you know, a little region out here, you know, like out here, I'm only cutting through 2 field lines, so the magnitude is relatively small there. That same area, if I put it here, I'm cutting through like 1, 2, 3, 4, like 4 field lines are going through that, right? So they're more bunched up there, corresponding to the fact that the electric field has a larger magnitude. So qualitatively, this is what we can tell from field lines. The more dense the field lines are, the higher the magnitude of the electric field. The more spread out, the lower the magnitude of the electric field. That's the way these pictures work. Yeah?
Does that mean that the magnitude of the electric field is relative to where you're measuring?
Yeah.
Okay.
It does. So remember last week we learned that the Coulomb field, if the charge is at the origin, it's just what? It's kq over r squared r hat, right? So this is the so-called Coulomb field. Let's draw the field lines for that. So I put charge q at the origin, and the field line picture here is really boring. It's just one this way, one that way, one this way, one that way, one this way, one that way, one this way, one that way. All right, I'll just do that many because I can do those relatively symmetrically. Now, if I do this right, they should be completely symmetric around the origin, right? And they go out like that. So the further out I go, the lower the magnitude, as is reflected in the formula, right? Because it's divided by r squared. The further we are from the origin, the lower the magnitude. All right, so, and of course, these pictures are just a, what's the word? Well, they're a 2-dimensional representation of a 3-dimensional reality, right? They're a projection. Because really, we should be thinking about something more like a hedgehog, right? Well, I don't know, a sea urchin. It goes like this, right? All possible directions. So if you think about this, if you can imagine, you know, enclosing the origin with like a sphere, right? Then if I enclose the origin with a sphere here, or if I enclose the origin with a sphere like all the way out here, right? Either way, the same number of field lines cut through that surface, right? Because the field lines only start where there's charge. If there's no other charge in play, then whatever charge comes out of the origin, whatever field lines come out of the origin, they keep going out. So no matter how big we make this sphere, we're always going to cut through these, you know, in my current picture, 1, 2, 3, 4, 5, 6, 7, 8 field lines. All right? So this is the first idea. So we can think about electric field lines to understand how electric fields spread out and how the magnitude decreases as we go further away from charge. All right? Now, to make this more precise, we need to introduce a specific quantity called flux. So flux, the flux of the electric field surface S, right? One way to think about it is it's the number of field lines, what's the word, poking through. There's probably a better word for that, right? Piercing, that's the word I'm thinking of. Piercing, probably misspelled that. You guys fix it for me. Piercing the surface, right? So like, that's kind of a transitory definition, right? Because if this were the way we defined it, it would be kind of annoying, right? Because it would depend on how I draw my picture. Do I draw it with 11 lines? Do I draw it with 8, right? We need something that's more concrete to define flux. And so what we're going to do is we're going to say, well, no, it's really equal to the, well, that's true, but, well, I mean, I just have to be, I need calculus here is what I need. So it's the integral over the surface of the electric field dotted with dA. So this is the so-called surface integral of the vector field E, the flux of E. It counts the number of field lines that go through the surface S. So like, let me give you some special cases. Which will be helpful to us. Like we can think of S as, you know, a subset of like a rectangle in a plane. Right, so like here's a picture. So here's my rectangle, right? And that rectangle has a certain area, all right? Area A, right? And I can draw the normal to that plane, right? So there's a certain normal to the plane. So I usually, dA is an infinitesimal area element that points normal to the surface. If you like, you could just, you know, put an n hat here if that makes you happy. But so that's perpendicular to that area, all right? Now what's the flux through that little rectangle? Well, that, we don't know yet because we haven't yet pictured the electric field, okay? So if the electric field looks like this, let's say, right? And I mean that the electric field's constant. So the electric field looks like that there, but it still looks like that over here. It's like always that same boring. So I'm supposing that we have a constant electric field, right? Like we found between the capacitor plates the other day, yeah? So for a constant electric field, the flux in this particular case, and by the way, we use the symbol we use for this is like big phi sub E for electric flux. So in this case, the electric flux would just be the electric field dotted with the area vector. And in here, area vector, I'm just saying like A vector is the area times the normal to the vector. This would be the area vector. It's a vector whose magnitude is the area and its direction is the normal direction. Okay, so another way I could write that is if we had the angle between the normal to the surface and the electric field, we could use that, right? What do you guys want to call it? We could call it like, I don't know, how about theta? Sound good? So that angle, the angle between the normal, then a formula for this would be like EA cos theta. And I know the picture's a little bit busy, so let me try to draw the picture like straight on its edge. If this is the area, if the normal is like this, and the electric field is like that, just looking at the rectangle dead on, yeah.
What does the I, the capital I with the circle in the E mean?
That's the electric flux.
Okay.
So this is a definition. It's a definition. Although truth in advertising, I haven't really defined the integral symbol at the top yet, have I? Yeah? I'm going to define it first by examples, if that's okay with you guys. And then towards the end of lecture, I will give you the straight formula for it in terms of integral calculus. All right? But largely speaking, there are like 4 examples we need to know in here. If you know those 4 examples, then you're pretty much good to go. So we need to know how to calculate the flux of a segment of the plane or the plane, electric field through like a plane. We need to know how to calculate the flux through like a cylinder. We need to know how to calculate the flux through like a sphere. There must be a 4th example. That might be it, actually. But I will give you the mathematically general way of calculating flux as well, because I think it's you should see it. Okay, so anyway, all right, guys. So like let's appreciate what goes on here. So special case, right? If the electric field directly goes through the surface, right? The flux is simply what? The product of the magnitude of the electric field times the area. Simple as that. And that corresponds to what I was saying about field lines a second ago, right? The larger the electric field, the greater the flux, right? Or if the electric field's constant, if you double up the area, you double up the flux. So that's essentially the same idea that was hiding in counting the field lines, all right? On the other hand, what happens if theta is 90 degrees? What's the electric flux from that? Is 0, right? So if the angle is 90 degrees, that means the electric field is tangential to the surface, and that does not count. It doesn't cut through the surface in that sense. We don't count it. It doesn't give us any flux. All right. This is a lot of the examples. Yeah.
And so to clarify, n hat is just the unit vector of the normal vector to that.
That is what I mean by n hat, right? So this is the unit normal vector to plane. So we could have a rectangle and a plane. That would be how that goes. All right. Another case, let's talk about cylinder. So let's see here. We could have a cylinder like this. All right. And let's suppose that this is the z-axis. All right. And here's your y-axis. Here's your x-axis as per usual. All right. And let's talk about a special vector field. Let's talk about a vector field, the electric field, which has the following form. It's equal to, like, you know, some magnitude which is just a function of r. I guess I should use s. My bad. S and then times s hat. So if you could look down the barrel here at the z-axis, then if you were to say fix your attention on a circle like that, the electric field would be like radially outward in this sense. So this is s hat. Now this s I'm introducing, guys, is the physics polar coordinate. It's x squared plus y squared. See, in physics we like to use r is equal to the square root of x squared plus y squared plus z squared. As you know, mathematicians have this perverse need to use rho for the spherical radius, but that's wrong. R is the spherical radius, right? But if r is the spherical radius, what's the polar r? Well, we need another letter, so we use s. All right? So s is the polar radius, and s hat is simply a unit vector field which points radially outward from the z-axis. Do you understand what I'm saying? So this is like a top-down picture. If I was so foolish as to try to draw the electric field, it would be hard to draw, but it would look something like, let's see here, so it's like radially outward. I don't know. I tried, guys. I tried. So it's just going directly out from the z-axis. I never can quite draw these things. Yeah? What would the flux of this electric field? So here I just mean that the magnitude depends only on S. All right? That's the start of it, but it's never the end of it. Let's see here. So, what's the flux in this situation here through this cylinder? All right, and I guess I should probably tell you, let's say the radius of the cylinder is r, and let's say that its height, you know, maybe it's going from z equals to L down here to z equals to minus L, since that's the way I drew the picture. All right? So as you look at it, the cylinder has 3 parts to it, doesn't it? The cylinder has what? It's got the top, right? It's got the side. And then, of course, it's got down here, it's got the base, right? Now, the convention is, when we calculate flux through a closed surface, that's with respect to an outward pointing normal. If it's a closed surface, it doesn't have any like openings, all right? So admittedly, the plane that I started with us is not a closed surface, right? But anyway. So here, the normal vectors, like this is my dA, goes this way here. Down here, dA goes like this, all right? And on the side, dA goes like this here, and it goes like this over here, right? In other words, a formula for the infinitesimal area element on the side of the cylinder is simply dA S hat. If you'd like me to be more calculus-y, not a word, you'll forgive me. You could do something like this, right? That's r d theta dz S hat. If you wanted me to do that, we could do that. Oh, I thought I'd written past the event horizon in here, but no. At NC State, we used to have this, like, well, this building's now demolished, but when I was there, we were in Harrison Hall, which was just like circular building, and there were classrooms that were like really shallow but really wide, and some of the chalkboards I think actually bent around they'd be curved classrooms. They were actually like sectors, and so like the chalkboard would kind of have a little bit of a curve to it, and if you got too far over here, you couldn't see what's on the chalkboard over there because it was like literally past it was bad. Now they've got some fancy new statistics building, which has got a 4-story atrium and all the niceties of modern corporate money. Anyway, so that would be the formula for. Now let me just, for the sake of specificity here, dA would be something like, you could do, say, dx dy, you know, z hat, and down here, if you want me to give you a formula, you could do something like dx dy minus z hat. All right. Now we don't even need all this formula stuff. I'm just throwing it out there, because I can describe to you what the flux is of this electric field through the cylinder without any kind of calculus at all, right? We don't even need calculus here. What is the flux of this electric field through the top and through the base? If you understand example 1, you should understand that the flux of this electric field is a big fat 0 through the top and through the base, because the electric field is going radially outward from the z-axis, right? So it's not cutting through the top or the base. So the flux of these two pieces is 0. On the other hand, the flux through the side of the cylinder, what's that? So we need the magnitude, the circumference, yeah. The magnitude at r, right? Because that's where we are. So I'm saying that, you know, this is distance r from the center, right? So the magnitude of the electric field is given to us to be E of r, everywhere there, all right? And we just need what? It aligns everywhere, right? This electric field is exactly it lines up with the outward pointing normal to the cylinder, right? So we would simply do, we just need the area of the cylinder. What's that? I'm not saying multiplication by r here, guys. I'm saying the electric field at r. Do you understand? So the area in this context would be what? We've got E, which is a function of r, times what? I think I heard circumference. I like that, 2 pi r. That would be this. If we took this cylinder, we just laid it flat, we'd have 2 pi r, this distance. And how high is it? What's that? L would be a good guess if I draw my picture differently, but I drew it from minus L to L, so 2L, yeah. So anyway, we get 4 pi r L times the electric field is equal to the flux of the electric field for this one. All right? Are we understanding? Are we? All right, the other example that is very commonplace is the sphere. So, aw man. Now this one we may need to, well, maybe we'll calculate this one with the math definition, but first we'll do it with physical reasoning, okay? All right, well, let's first do a really easy one before I get to the harder one. That was example 1. Well, I forgot my numbers. That was example 1. This was example 2. This was example 3. This was example 4, I believe. So I think we're on example 5. All right, so here's a really easy one. Suppose you've got electric field is equal to E naught times U hat, where U hat is fixed constant vector. So this is just a fancy way of me telling you that the electric field points, it's constant, right? It's pointing in the U hat direction no matter where you go. It's a very boring electric field. Then I take a sphere, right? A sphere of radius r, right? Sphere of radius r here. You can put it wherever you want. We could center it at the origin. I usually do that, you know. The question then I have is, what's the flux of the electric field through the sphere? Yeah? So if you think about that, we can envision the electric field whichever way you want, right? Because without loss of generality, we can assume U hat's X hat, for example, or Y hat. I mean, why not? So let's, picture E as being like this, right? We could do that. And if you do that, think about this. The sphere has 2 halves, right? This half, the right half, you have dA like this, right? For the right half. On the other hand, over here, you've got dA like that, right? The normal, I guess I should have drawn it here as there. Let me be less ambitious. Let me put it there. So my point to you is that you'd get, so on this half we get a positive flux. See, because the electric field lines would be cutting through the sphere in the same direction as the outward pointing normal, right? So as I have it set up, positive flux from the electric field going through the right half of the sphere. But on the other hand, the electric field would be doing what? would be going opposite the direction of the normal over here, yeah? And in that situation, that gives us negative flux. So, negative flux. More to the point, if you want to envision it, every field line that comes in here on this side, boop, boop, comes back out over here this side, boop, boop. All right? If it comes in here like so, boop, boop, it comes back out over here, gadook. Or maybe if you want to adopt like maybe a Kung Fu Panda style sound effects, you can say skidoo or something like that. I can't do it, but anyway, you know what I'm talking about. You guys have all seen it. So every field line that comes in, one side goes out the other, right? Or the field line is irrelevant because it's down here. Yeah? So what's the flux through the sphere of this constant electric field? In this example, the flux is a big fat 0. Because the flux through the left and the flux through the right are equal and opposite by symmetry. Now there's a deeper reason for this that we'll discover next class, all right? But for this class, I'm just trying to set up the concept of flux, all right? We'll talk about the physical law that corresponds to this soon enough. The Coulomb field is our example 6. So let's calculate the flux of the Coulomb field through a sphere. All right? And so I'll just draw it two-dimensionally. So here's my Q. Here's my sphere of radius r. Right? And notice that the electric field and the outward pointing normal to the sphere, they are in agreement. They are parallel. These arrows I just drew, they could either be the electric field line, the electric field at the surface of the sphere, right? Or they could be the normal to the sphere. Either way, they're the same, right? So like the flux of the Coulomb field through the sphere of radius r should be the magnitude of the electric field there times the area, right? This is true, why? Because the electric field is parallel to ds. Well, excuse me, dA. I use ds vector in my calculus, so it's messing with my head, okay guys? But dA vector. If you had calculus 3 with me, I use ds vector for the surface area, infinitesimal surface area element. But anyway, because the electric field is parallel to the surface in the sense of parallel to the normal to the surface, the flux is just the magnitude times the area. Now I can say magnitude, right? Because by symmetry, the Coulomb field, well, by the formula, the Coulomb field has the same magnitude at a given radius, right? If we put the charge in the middle. What is the surface area of a sphere? What's that? 4 what? 4 pi r squared, right? So we've got E times 4 pi r squared. In fact, what is the electric field? What's the magnitude? Right here, right? So we can do a little bit more. We can say, aha, well this is really, you know, kq over r squared times 4 pi r squared. Whoa. Check that out. The r squareds cancel. And we've got what? We got ourselves a 4 pi k q, yeah? But what is 4 pi q? What is 4 pi k? Remember what k was? K, by definition, was 1 over 4 pi epsilon naught, yeah? So 4 pi k is what? Yeah, 1 over epsilon naught. So that is exactly q over epsilon naught. So in other words, we just calculated that for the Coulomb field, the flux of the electric field is equal to the charge divided by epsilon naught. Which is justification, it's verification. The things I told you at the start of class are not crazy. right? The flux is the number of field lines. Well, the flux is proportional to the number of field lines, whatever system of field lines drawing that you adopt, all right? The flux is not ambiguous. The flux is the magnitude times the area appropriately weighted according to this notion of integration I haven't carefully written down yet. That's not an ambiguous thing. The number of lines that you draw, that is a choice for your diagram, all right? But this here says the flux is equal to the charge divided by epsilon naught. So like I said, if you double the charge, you double the number of field lines. See it? Yeah. This is what's called Gauss's law. Now Gauss's law is more general than this, but this is our first example of Gauss's law. Think about this. If you assumed this was true, and you knew about the general direction of the field being like radially outward for the charge, this formula would derive that magnitude. We'll look more at that like next class, but anyway. Let's do a little bit more flux. I guess I probably at this point probably owe you the proper definition of flux because I've just been giving you examples and giving you some intuition on it, but I probably should actually define how we actually calculate the integral of the EDA in the unfortunate event that you run across something other than our token canned list of 4 examples that we tend to use in here. And the definition that you should learn in your Calculus 3 course before too long is simply this. If your surface has parameterization x of, say, uv vector. So what I'm saying is you've got some parameter space down here, uv space, and this is a domain. Your parameterization map x takes it and puts it up here on some surface. So up here is x of d. This is the surface. All right. So d is the parameter space. X is the surface that I'm parameterizing. Then relative to that surface, you can define like partial velocities. See, you've got x sub v, and over here you've got x sub u, meaning partial x, partial v, and partial x, partial u, like so. Those will be tangential to the surface. If you take the cross product of those two partial velocities, what do you get? If these are both tangential to the surface, what's the cross product? The normal, right, that's normal to the surface. So the cross product of the partial velocity gives you the normal to the surface, and that's the thing you want to set up the flux integral on. And so it turns out that the formula for the electric flux through the surface which I just parameterized is the following. You just do the double integral over d, you take E, you shove in the parameterization, and you simply take the dot product with the partial derivative of the parameterization cross the partial derivative of the parameterization, like so. Integrate that thing over du dv, and that's it. So that's the formula for the flux. This is what you're learning in Calculus 3. This is the end of Calculus 3. The last about 20 to 40% of your Calculus 3 should be all about understanding this calculation and how to do it. All right? Your book is horrible. It doesn't give proper notation in your book. Your book is stupid. Stewart is stupid. I'm sorry. It's just the case. It was not written by a physicist. Physicists care about these things. Mathematicians don't really care that much about Calculus 3, honestly. So if you do care more about these things and you want to see how to understand like this kind of integral works in a more physicsy notation, please look at my Calculus 3 notes. There's tons there. All right, anyway. So like for the sphere, when you work this out, so this contraption right here is what I would call dA. All right. So for instance, if you were to calculate for a sphere, if you used, say, the usual angles, I don't know, theta, phi, something like r Well, if I use the math ones, it's r cosine theta, sine phi, r sine theta, sine phi. These are not the physics engineering. Physics and engineering tends to have the roles of theta and phi swapped, so watch out for that. But if you do this, this is the parameterization of a sphere using spherical coordinates. And basically, if you calculate this dA for this thing, what you end up getting is r squared, if I remember right, sine phi, and then you got yourself like a d theta, d phi, and then the direction, let's say, is, well, oh, I'm sorry. I guess I'm using math notation, so I probably put a rho hat. This is actually what that works out to. And so what happens, the Coulomb field in this notation is like kq over rho squared rho hat. So when you calculate E dot dA, you just end up with, well, anyway, I may not go further into this. Maybe I'll actually go through this calculation in gory detail. It takes me about 10 minutes of some other class. I'm not going to do it today. I think we've done enough for today. Do I expect you to know and implement this definition? Obviously not. Am I going to teach you how to do double integrals in here? No, I'm not. So why am I writing this? So that you know what the actual definition is, because all of the things I showed you are special cases. And I'd like you to know that there is a well-defined procedure for calculating flux in the case that you're not in one of these special cases, but you have to do calculus, all right? And you have to, there's a dot product here. It matters because, like, it's not just about the magnitude changing, it's about the direction of the vector field aligning with the surface, right? It's both magnitude and direction can vary in the proper full definition of flux. The examples I looked at today, either the direction was contrived so that it always lined up with the normal, like in the cylinder example or the sphere example, or the magnitude was so silly that we could use a symmetry argument, like in example 5 to see it's 0, right? Anyway, so next class, I'm going to start by stating Gauss's law. And then we're going to use Gauss's law and this concept of flux to calculate the magnitude of the electric field for many of the examples we did last week, but it's actually much easier with Gauss's law. So it's the next big thing to learn. So anyway, that's out.